Hello and welcome to week 10 or chapter 9 for statistics 1. This week we're making a big transition to something that mathematically is not very complicated, but it's a pivotal concept in statistics in general. And it's called sampling distributions of the mean or central limit theorem, which is a key concept for it. So for this video, we're going to do a little walkthrough of what the whole premise is for this chapter and what it means moving forward. So, in previous chapters, we studied the mean, the standard deviation, the normal distribution, and what that curve looks like, how probability is a concept that's attached to the normal distribution. So, for example, if we had, and I'm going to take the example from test 1 from previous in this course. And in test 1, we had a data set where exam 1 was a group of test scores. And those test scores of that population of approximately 60 students had a mean of 85 and a standard deviation of 9.85. The mean, if you recall, is a measure of central tendency, and that's where the numbers or the values tended to be centered at. Some of them are higher than 85, some of them are lower, but the majority of them were around 85. That was our mean. And the standard deviation is a measure of spread, or how varied the numbers are. And 9.85 means that, and when we translated that to the normal curve, we have a normal distribution, symmetrical about the mean. So 85.03 was the mean of this distribution, or the center point. And if we go out one tick mark or one standard deviation either direction, I added and subtracted the 9.85 to the 85.03 to get these two values. So I have a part of the entire distribution that is within one standard deviation of the mean, one increment above and one increment below. And on the normal curve, and we had the area under the curve, which correlates to the probability of you selecting an item within that range. We know that about 68% of the time, if you selected an individual at random from the group that produced this data, 68% of the time you are going to get a data point between 75.18 and 94.88. And again, that's if you're selecting one at random. Moving forward, though, we're going to take a look at what can we expect if we had a population like this, but if we selected a group of data points from it, where can we expect the mean of that group to fall within this distribution? So we're going to take a look at this question here. What if we took samples of 36 randomly selected scores from that original population and calculated the sample mean of those 36? What would that look like? Where can we expect the average or the mean of these 36 randomly selected points to fall in this distribution? And it turns out that the means of these, if we continue to do this, the means are going to fall pretty close to what the actual population mean is. So we might get, we might end up getting one group that has a mean a little bit above an 85. We might get one a little bit below. We might get one right on it. And if we continued this process of repeatedly taking samples of 36 and then finding the mean of those 36 and plotted it with that same axis that we have here, the majority of the time, the values are going to be very close to the true mean. And it's going to end up forming a normal distribution just like this one, centered at the mean, but instead of it being spread out, it's going to be much more clumped together. And the majority of the points are going to be much closer to the actual mean than they were when the distribution was of individual points. Let me rephrase that. This normal curve is of each of the individual data points. So it's a little bit more spread out. This normal curve, not very pretty right here, but this normal curve is going to be centered at the same, but this is made up of the averages of groups of 36 of data points from this population. So they're going to be much more clumped together. And the central limit theorem is a theorem that you can read in the text, and it states this. As I continue to build this distribution of the sample means, this distribution is going to be normal, and it's going to be centered at the true mean of the original population. But the standard deviation of this distribution is going to be smaller, tighter than this original. And the two formulas you need to know are this. And I'll go through the symbolization of the two. The population mean, which is mu, the Greek symbol mu, lowercase, of the sample means. I have x bar, which means I have a sample mean. In this case, I took a sample of 36, found its mean. I take another sample of 36, found its mean. If I continue to do that and find all of the possible combinations of 36 out of this original population and find their means, and I find all the averages of those, the averages of the averages is going to be the same as the average of the original one here. And I'll get to the point of why that's important later. The second part is this. What about the standard deviation of this? The standard deviation of the sample means, which is symbolized with the lowercase Greek sigma, little pigtail look, of the sample means. So this x bar is indicating that I am not finding the standard deviation of each individual point. I'm finding the standard deviation of the averages of groups of 36. It's going to be equal to the standard deviation of the original group divided by the square root of the sample size. So in this case here, I have 9.85 as my sample mean. And I had 36 as my sample size, so the square root of 36 is 6. So when I divide 9.85 by 6, I get approximately 1.64. So that means that instead of having a standard deviation of 9.85 for the individual scores and it being that spread out, which means 68% of the time I can expect an individual score within one standard deviation, my values are going to be much more clumped together. With the increment, instead of being 9.8, it's going to be an increment of 1.64, a lot tighter together. And that tells me that 68% of the time, I can expect to get, if I take a random sample of 36 points out of this population and find the mean of those 36 points, 68% of the time, I can expect it to be within 1.64 of the original population mean. Much more tighter group. And I can carry that out one more further, that I can expect it to be 95% of the time within 2 of these increments, about 3.2, which is much more tighter than this original spread. So that's what the central limit theorem is. These are the key formulas you need. And for this chapter, I highly recommend you reading the chapter without worrying about the math of it and understanding the concept that we're taking a shift now from, instead of taking a look at individual test scores, we're looking at what are the characteristics of the averages of samples of those test scores, because this is what we're going to need for the second half of the course. This is making a transition from the first half of the course, which focuses on simple, meaning basic statistics and just raw statistics without much interpretation, to now we're going to, after this chapter, shift towards inference, which means when we do find some of the statistics, like the mean and the standard deviation that we took a look at in the first half of the course, what can we do with those tools to make predictions about a population that perhaps we don't have the ability to actually study the entire population, but we can only take a sample. So that's what this chapter focuses on. There's the reading of the text. There are also a couple of videos for this week that I highly recommend you watch, because the concept of the central limit theorem is a key one for the rest of the course. Good luck with the week, and again, feel free to put any posts on Slack or via email if you have any questions. Thank you.